Let's talk about flow. So here's what's happening. We've got a vector field. So quick recap there. You input a location in the xy plane, and you output a vector at that location. Now, specifically in this case, we're talking about a velocity vector field. So in the context of flow, at least as an application, we're thinking about this vector field as a velocity vector field. So at some location, x comma y, you're going to output a velocity vector at that location. And typically those vectors are going to be given to us in the form of something I plus something j. Now, because we're specifically talking about a vector field, we can also define this velocity vector field such that the f1 is going to be the derivative of x with respect to t, and f2 is going to be the derivative of y with respect to t. That is, if we just had a regular vector field, maybe we'll call it, instead of v for velocity, which we call it? We'll call it w at xy. So if we had a w at xy vector field that was something I plus something j, now we're taking the derivative of that. So the derivative of w vector field would be a velocity vector field. And to get that, we're of course going to take the derivative of x and the derivative of y to get that velocity derivative vector field. So that's what we got. In your brain right now, just imagine a vector field. Now, the flow would be a parameterized curve through that vector field. So if, I think Milos used the idea of a seed floating on the top of a water in a river or something. Like imagine if you floated down the Salt River, you drop a seed or a piece of grass or whatever, and it just follows the flow. It follows the velocity vectors at any location. It's going to move in the direction of the flow of the stream at that point. So the flow is going to be the position of the point in that vector field at any time t. So now this is where it gets, you gotta get a little grip on this. You're gonna see it again next week, but r of t. So imagine taking r of t and substituting it into, composing it with f, that vector field. So what we're saying is, inside that vector field, on that curve, that's where we are. Okay, so let me that's the setup, but let me give you an example now. I'm going to actually go back for this first thing. I'm going to go back to one that was presented earlier. We were given a velocity vector that was negative yi plus xj. So at any point x comma y, you output a vector v. So I'm going to give you a new tool in this case. Here it is. So if you Google p-plane or d-field, whichever one you might want, direction field or phase plane, just put that into your Google p-plane. This will be the first thing that comes up. And then p-plane is a Java thing, so you'll get some, at least I do, get some not errors, but warnings about, do you really want to download this Java thing? I said yes. And so I get this. Where is it? So when you launch the p-plane, you get several windows. One window is where you can type in some of the details. Like in this case, notice it's x prime. I know it's hard to see that, but x prime equals negative y. Y prime equals x. Let me take you back. Remember that the definition is this velocity vector field is f1i plus f2j, where f1 is x prime of t, f2 is y prime of t. And so x prime of t in this case is negative y prime of t is equal to x. So back to my graph here. Well, there's the graph. Back to my, so x prime, I know it's hard to see, but there's a little tiny prime there. X prime of t equals negative y prime of t equals x, and boom. And if you think through, I won't take the time here, but we had some discussion about, like, why does this vector field make sense? I'll let you make sense of that later, but there it is. So now what we're imagining is the flow of this vector field is just the family of curves that would pass through any point and follow that vector field. So like, that's the cool thing about this is you can click on a point and it'll show you the flow. It'll show you the trajectory through that vector field. And so what we're looking for is a way, an algebraic way or a symbolic way to say all of these orbits, as they're called in here. Let me show you something. Where is it? There it is. So you could delete an orbit by just clicking on it, or you can delete all the orbits. So that's what we're looking for, is we're trying to find a way to say, hey, look, at any point in this vector field, the flow, that seed going through it would follow this circular path. What would that circular path be? That's what we're trying to identify. All right, so back to the work. So what we now know is that x prime of t is equal to negative y, and y prime of t is equal to x. Keep in mind, f1 is x prime of t, which is negative y. f2 is y prime of t, which is x. Now remember, we're looking for this flow as r of t is x of ti plus y of tj. So we need x of t and we need y of t. Now this is really the system of differential equations that they're talking about in the text or in Milos's videos. Now he uses some different notation than I'm using here. I'm trying to present a different way of thinking about it. But this is a differential equation because look, it says the derivative of x, like dx dt, is equal to negative y, and dy dt is equal to x. Can you find x and y? All right, so what we're thinking about here is I need something that goes here so that when I take the derivative of this something, I get the opposite of this something. And when I take the derivative of this something, I get that something. Now, this shouldn't have to be a big computational thing. It should be like a ponder. So when I take the derivative of this something, I get the opposite of this something. And when I take the derivative of this something, I get that something. Now this is like where your Calc 1 would come in. See if this rings a bell. If you had back in Calc 1 the sine function, the derivative was cosine. Or back in Calc 1, if you had a cosine function, the derivative was negative sine. So let me say it again. If I take the derivative of this something, I get the opposite of y. I get the opposite of this something. And if I take the derivative of this something, I just get that something. Sounds like cosine does that. So if you take the derivative of this something, you get the opposite of this something. Well, let's say this something down here was sine. The derivative of cosine is the opposite of sine, and the derivative of sine is cosine, so it fits this pattern exactly. Let me just say that one more time to make sure that it's good. So x prime of t is the opposite of y. So if x is cosine, the derivative of cosine is negative sine. It's the opposite of y. And the derivative of y is x. The derivative of sine is cosine, which is x. Now there is, to get like the full family of functions, you could have a constant multiplier on this thing too. I'm just using a as a parameter here. So anything times cosine of t, the derivative will be negative a sine of t, the opposite of y. And the derivative of a sine of t is a cosine of t, x exactly. So our flow in this case, our r of t that we're looking for is x of ti, so a cosine of ti plus a sine of t j. Now, back to this. See if this makes sense. Also, connect it back to the parameterized curve stuff you did earlier. A parameterized or vector-valued function involving sines and cosines certainly is going to produce your circular motion through the plane. And with a coefficient of a, it's just going to produce concentric circles depending on the value of a, which excuse me, which should resonate for what we were seeing back here. But also, just to show another piece of technology here, we could also do this in Desmos. So notice what I've done here in Desmos is put in as an ordered pair. This is how you do parameterized stuff in Desmos. Put in the ordered pair a cosine t, a sine t. But I want you to see it slowly. So I said allow t to vary from 0 to k. And then I'll make a slider for k. And then there's also a slider for a to show the series of concentric circles, the family of flow lines, the flow of this vector valued function. So here they come. So right now I've got a is 3, so 3 cosine t, 3 sine t. Doesn't that look like the seed passing through that vector field following the vectors? And if you change a to something else, you get the same idea, but radius of now 4. Or here, I'll just leave it completed. As a changes, you just get the series of concentric circles, the flow of that vector field.